Welcome! Today, we are diving deep into Learning Module 10. We're going to go through a step-by-step guide on how you can test, use, and even tweak a simple linear regression model, just like a pro analyst would.
So here's the game plan. We're going to start with a real-world question that every analyst has to face. Then we'll introduce the tool for the job, and we'll cover the whole shebang, from checking the rules to making predictions, and even what to do when your data gets a little tricky.
All right, let's jump right in. Before you can do any kind of analysis, you've got to start with the why. What's the fundamental problem we're actually trying to solve here?
And here it is, the big question. Does spending more money on new projects, capital expenditures, actually lead to making more money? It seems obvious, right? But how can we prove it? More importantly, how can we put a number on that relationship? Okay, so to tackle this, you got to start with the data. What we've got here is a small sample, just 6 companies. For each one, we see their capital spending, or CapEx. That's going to be our independent variable. And we see their profit, measured here as return on assets, or ROA. Now, you can kind of eyeball it, right? It looks like when CapEx goes up, ROA goes up too. But looks like isn't good enough in finance. We need a much more rigorous way to confirm this. And that brings us to our main tool for the day. This is where simple linear regression, or SLR for short, really shines. So what is simple linear regression? Well, at its heart, it's just a technique for drawing the one best possible straight line through all those data points we just saw. And look, this line isn't expected to hit every single dot perfectly. That's not the goal. The goal is to capture the average relationship, the general trend between our two variables. And it all comes down to this equation. This is the engine of the whole thing. You've got Y. That's the thing we're trying to predict, our ROA. And you've got X. That's our predictor, the CapEx. The B0 and B1, those are the numbers our model is going to figure out for us. They basically define the line, where it starts and how steep it is. So you might be asking, how does it find that one single best line? Well, it uses this really clever method called least squares. Just picture this. You draw any random line through the data. For every single data point, you measure how far away it is from your line. That distance, that's your error. Then, you square all those errors and add them up. The best fit line is the one line, the only line, that makes that total sum of squared errors as tiny as possible. It's literally the line that's the least wrong across the board. Okay, this next part is absolutely crucial. Before we get all excited about our shiny new model, we have to do a kind of pre-flight checklist. See, simple linear regression isn't magic. It only gives you reliable answers if 4 key assumptions are met. And here they are, the 4 big rules of the road. 1, the relationship has to actually be a straight line. 2, the errors have to be spread out consistently. 3, the errors can't be related to each other. And 4, those errors should look like a classic bell curve. If you break any of these rules, your model could give you results that are just plain wrong. So how do we check for this stuff? Well, one of the coolest things is that you can often just see it. After you build the model, you take all those little errors, we call them residuals, and you plot them. If what you see looks like a random mess of dots, like a shotgun blast on the left, you're golden. That's good. But if you see a clear pattern, like that smile or frown on the right, that's a huge red flag telling you the real relationship isn't a straight line at all. And here's the check for that second assumption, homoscedasticity. Yeah, I know, it's a mouthful. All it means is constant spread. We want our errors to be scattered in a nice, even band, just like you see on the left. What you don't want to see is that cone or megaphone shape on the right. That's called heteroscedasticity, and it's bad news. It means your model is more certain about its predictions in some places than in others, and that's not what you want.
So, you've done all the hard work and you've built a regression model. But the big question is, can you actually trust it? See, building the model is really just the beginning. The real job is making sure it's solid and then using it the right way to make smart decisions. Let's get into it. Let's start with the big picture. Is our model any good at all? To figure this out, we're going to use a running example from the text, trying to explain a company's return on assets, that's ROA, by looking at its capital expenditures, or CapEx.
All right, so let's say our model passed its pre-flight check with flying colors. Now it's time to give it a report card. Just how good is it? How well does it actually explain what's going on with our data?
Okay, first, we need to understand something called the sum of squares total, or SST. The easiest way to think about this, it's the whole puzzle. It's the total variation in the return on assets across all the companies we're looking at. This is the big mystery we're setting out to solve. Next up is the sum of squares regression, or SSR. So if SST is the entire puzzle, then SSR is the part of the puzzle that our model actually solves for us. It's the amount of variation in ROA that we can pin directly on the changes in CapEx.
And whatever's left over, well, that's the sum of squares error, or SSE. These are all the puzzle pieces still scattered on the table, the variation that our model just can't explain. These are the errors. And of course, the whole point of building a good model is to make this leftover pile as tiny as we possibly can.
Now, all of this comes together in a super handy tool called the ANOVA Table. That stands for Analysis of Variance. Think of it like a scorecard. You can see right here that the total variation is 239.50, and look how it splits up perfectly. 191.625 is explained by our model, and the leftover 47.875 is what's unexplained.
The ANOVA table just splits that total variation into two buckets: the part that our model can explain and the part it can't, the leftover random error. And obviously we want that explained bucket to be as full as possible.
With those numbers, we can calculate one of the most famous metrics in all of statistics, R-squared. It's a really simple idea. You just take the variation you explained and divide it by the total variation. The number you get tells you, as a percentage, exactly how much of the puzzle your model has solved.
And for our model, we get an R-squared of just over 80%. Now, if that is pretty strong, it tells us that CapEx explains a huge chunk of why ROA changes.
It means that 80% of the entire story of why return on assets is high or low for these companies can be told by just one thing: their capital expenditures. That is a fantastic report card.
But here's the million-dollar question. Is this a real relationship, or did we just get lucky with our data?
To answer that, we turn to the F-test. The F-test is like a statistical judge. It compares the variation our model explains to the variation it can't.
This number answers a slightly different question. Is the relationship we found real, or do we just get lucky with our data? Could this all be random chance? A big F statistic, like this 16.01, basically shouts, "No way this is random." It gives us confidence that our model is actually picking up on something real.
And the high F statistic, like the 16.01 we have here, is the judge banging the gavel and telling us the model is legit. It has real, statistically significant explanatory power.
So here's the best way to keep them straight. R-squared tells you how well the line fits the dots you already have. The F-test tells you whether that line is actually useful for anything. Think of it as fit versus significance. And you absolutely need both to have a model you can trust.
So we know the model works overall. That's great, but now we need to zoom in and check our key ingredient. Is CapEx times itself a significant predictor of ROA? Let's find out. This is where the t-test comes in. Here's a helpful analogy. The F-test tells you if the whole cake tastes good. The t-test comes along and checks each individual ingredient, the flour, the sugar, to make sure they're doing their job. In a simple one-variable model, they kind of do the same thing, but this distinction becomes absolutely critical later on when you're dealing with multiple variables. Now, we don't just guess about this. To test our slope coefficient, we follow a very disciplined 6-step process. This structured approach is what makes sure our conclusions are statistically sound and totally defendable.
So here's the bottom line. After running the numbers, our calculated t-statistic is about 4.00. The critical value, our line in the sand, was plus or minus 2.776. So our number is way beyond that line. That means we can confidently reject the null hypothesis. it's a slam dunk. We have strong proof that CapEx has a significant, real relationship with ROA.
Okay, so we've built the model, we've checked the rules, we've graded it. Now for the fun part. Let's actually put this thing to work and make a prediction. This is where it all pays off.
After all that number crunching, here's what our final model looks like. It all boils down to this simple formula. And that 1.25, that's the slope, and it's the real hero of the story. That number tells us that for every single 1% increase in CapEx, we can expect, on average, a 1.25% increase in return on assets. That is a powerful, actionable insight.
So let's put it to the test. Let's say an analyst is looking at a company and their forecast says its capital expenditures are going to be 10%. What does our model predict for its profitability? Well, we just plug the number 10 right into our equation. You take 1.25 times 10, add the 4.875, and boom, our predicted return on assets is 17.375%. But, and this is really important, a smart analyst knows no model is a crystal ball, so they'll also create a prediction interval, basically a range of likely outcomes, to acknowledge that there's always a bit of uncertainty.
We call this a point estimate. But let's be real. Any good analyst knows a single number is never the whole story.
Exactly. You have to ask, what's the margin of error? Because every model has some uncertainty built in. It's never going to be perfect. So instead of just giving one number, we need to create a prediction interval. This gives us a much more realistic range of possible outcomes.
So what makes this range, this margin of error, wider or narrower? Well, it boils down to three main things. First, how much uncertainty does the model have to begin with? Second, how much data did we use? Smaller samples mean more uncertainty. And third, how far from the average are we trying to predict? The further out you go, the shakier your prediction gets.
For our example, after all the calculations, we end up with a 95% prediction interval. So while our single best guess is 12.375%, we can be 95% confident that the actual ROA will land somewhere between 2% and 22.75%. You see how much more useful that is? It's a forecast that actually accounts for real-world uncertainty.
But you know what? The real world is rarely a perfect straight line. Things get messy. So what do you do when the data throws you a curveball? Well, this is where the pros separate themselves from the amateurs. They know how to adapt.
And check this out. This is such a great example of how flexible regression can be. On the left, you see what happens when you try to force a straight line onto data that's clearly curved. It's a terrible fit. But you don't just throw up your hands and quit. The pro move is to transform your variables. You can do things like take their natural log, and that can magically straighten out a curved relationship. Now you can fit a line to it, like you see on the right, and get a much, much better model.
First, you've got the Log-Lin Model. This is your go-to model when your Y variable, the thing you're trying to predict, is growing at a constant percentage rate. The classic example is modeling a company's revenue over time. It's a perfect fit for that kind of exponential growth.
Then there's the Lin-Log Model. This one works beautifully for relationships that have diminishing returns, where the effect starts out really strong but then begins to level off. Think about the link between sales volume and profit margins. That's often a great candidate for a Lin-Log model. And finally, we have the Log-Log Model, where you transform both variables. What's so amazing about this one is that the slope coefficient becomes a direct measure of elasticity. It tells you that a 1% change in X leads to a certain percent change in Y. This is incredibly powerful and used all the time in finance and economics. So we've gone through the whole workflow. We've evaluated a model, tested its parts, used it to predict, and even learned how to fix it when the data gets curvy. But the journey of a really sharp analyst, it never truly ends. Even when you have a great model, the final, most important step is always to ask yourself, what am I missing? What other variables might be telling the rest of the story?
So when you really think about it, what have we learned? A simple, straight line is an incredibly powerful tool. But what hidden truths, what other relationships could you uncover now that you know how to build it, how to test it, how to grade it, and even how to adapt it when things get weird? That's the real power here. It's not just an equation, it's a way of asking better questions about the world.